The electrical RLC circuit, RLC and the source of EMF, that circuit is said to be analogous to the mass spring dashpot and force or displacement driver mechanical system. And the analogy comes out when we write down the equations for the two systems, component by component, and then combine the equations for each system separately into maybe one single system equation. That is when the analogy or the similarity between the two different physical systems comes through. We can spend a few minutes on the electrical system with the RLC and the electromotive force as the four components. You will be all able to write down the equations for the four components separately. We had started off with one of the equations, namely the equation for the resistor, but one can write down, and I will do that, the equations for the remaining three components. So here are the equations: VR equal to RI, VL equal to L di dt, I C equal to C dV dt, and V for the source VE is equal to some function E. Actually, I should be a little more careful here. I should have used symbols which indicate what component or element of the circuit or network they are associated with. Thus, I have written a VR indicating that it's a voltage associated with the resistor R, or the resistor, physical device resistor R, and this voltage at any moment of time is given by the product of the resistance of the resistor, a positive number expressed in units of ohms, multiplied by the current in the resistor, and therefore I should write, strictly speaking, IR, I subscript R, meaning it is the current in the resistor. And again, to be absolutely correct, I should write VR of t equal to R into IR of t. The voltage across the resistance, as we say, at any moment of time t is equal to this parameter of the resistor called the resistance multiplied by, or multiplying the current in the resistor at time t, IRT. So this is the equation for the component of the network, a component which is called a resistor. Now at this point, note one thing very clearly, and I will go on emphasizing this a number of times, because otherwise a lot of confusion can occur. Now first of all, there is the actual physical thing or device called a resistor. Here, for example, is a particular resistor of a particular kind. This is what it looks like. Now you know that resistors can have various appearances. Here are some more resistors which look different from the one that I started with. Here is a one that is known as a wire wound rheostat. It is a much bigger thing, and one can see the wiring more or less very clearly. Whereas here is a very small resistance which looks like a very small cylindrical thing. It's not, one does not know what's inside it, and if you did not know what it might be, you would not even guess that it's a resistance or it's a resistor. Certainly there is no wound wire inside that. So there are those physical objects or things or components called resistors, which one finds in the laboratory on the shelf or one can go to the market and buy them. They are made or manufactured also. And as you know, each one of these resistors comes with a value, what we call the value of the resistance of the resistor. Typically it will be expressed in ohms, but in some cases kilo ohms or even mega ohms, and very rarely maybe milliohms. So here, for example, is a resistor whose resistance value is 1.3 kilo ohms, and all of you should be familiar with the way in which this value is marked on the resistor, not numerically as 1.3 kilo ohms, but in terms of some bands of particular colors. So here is a 1.3 kilo ohm resistor, which is very small in size, and as you can expect, you can't pass a very large current through it, otherwise the heat that is produced in it will burn it up. So here is the practical thing which has a number called a resistance, or the resistance associated with it, expressed in some unit such as ohm or kilo ohm and so on, having a particular appearance. It has some weight, size, and also along with it go some limitations, like the current in it should not exceed maybe 10 milliamperes or 100 milliamperes. Certainly the current in this tiny resistor cannot be maintained or kept at a level of say 10 amperes for even a moment of time. The heat produced will be so large that it will just heat it up and burn it. So here is a physical device which has all these aspects. It looks like this, it has weight, it has volume, and there are limitations associated with its use. Of course it costs something, but for us from the electrical engineering point of view, what matters at the moment is only its resistance, a particular number denoted by R, or R with a subscript like R1, R2 if there are two resistances, and so on. And we are making the assumption here, this is the important fact that one should be aware of and note, that this physical thing can be described, or part of its behavior can be described by means of an equation like VR of t equal to RIR of t, where in this case R would be the number 1.3 into 10 raised to 3 if I is a number which represents the current in the resistor in amperes, and VR is a number which represents the voltage across it in volts. And so you have volts equal to ohms into amperes. I should not have said I said 1.3 into 10 raised to 3 because the resistance was 1.3 kilo ohms. If I have the current in milliamperes, the resistance in kilo ohms, then the product comes out to be voltage in volts. Now if this resistance is say heated up, either because of heavy current flow in it, or you keep it near some other source of heat, then will it continue to be described by this equation V equal to RIT with R equal to 3 into 10 raised to 3, or if I cool it, if I put it in contact with a very cold mass of ice, let's say, will it continue to have a resistance of this same value? As we all know, this is not the case. The resistance value of a resistor will depend upon the temperature of the resistor also. So we are making the assumption that the resistance is operated in such a way that its resistance is given by 3 into 10 raised to 3 ohms. This is only an idealization, in the sense this is only in our concept or idea about it. That is, we like to think that the resistor behaves like this, V equal to Ri with R equal to 3 into 10 raised to 3. What we think will be correct, of course, or not too far wrong, hopefully most of the time, And so there is another aspect of it which we must remember, that is, this value 3 into 10 raised to 3 is to be taken with a pinch of salt, in the sense it is not asserted that the resistance value is exactly 3 into 10 raised to 3 ohms, even if the bands on it may indicate that it is, say, 3 into 10 raised to 3, or rather 1.3 into 10 raised to 3 ohms. No matter how good a quality a resistance one may, or a resistor one may buy, and this is associated with what is called the precision, this value 1.3 into 10 raised to 3, by the very nature of it, cannot be 100% precise. In a course on electrical measurements, of course, you would have looked at methods of measurement of parameters like resistance, inductance, capacitance, and also of physical quantities like voltage, current, frequency of alternating supply, and so on, magnetic flux and what not. So suppose we go to a laboratory and make actual measurement. So set it up so that some current flows in it, measure the voltage across it, measure the current in it. Will we find that the voltage number in volts will be exactly equal to 1.3 into 10 raised to 3 multiplied by the current number? No, and in fact for more than one reason, because just as there is this problem of what is exactly the resistance of the resistor, is it that specified value, and there is the question of precision. In fact, when you buy a resistor, you should ask about the degree of precision, or you should buy it knowing what will be the precision. Is the value going to be 1.3 into 10 raised to 3 within plus minus 10% or 5% or 1%? Because this is all that can be guaranteed of a ready-made resistor. Of course, if you wanted to make a resistance 1.3 into 10 raised to 3 ohms, and wanted to be more precise of it, you could choose wire and wind it yourself, choose an appropriate length of the wire, and so on and so forth. And therefore you may have more precision than is commercially available. In principle, you can make a resistor of resistance value which is within plus minus 0.1% of what you think it could be. But commercial resistances or resistors don't come with that kind of precision. Obviously, it is going to cost you more if you want a more precise resistor. So that's only one part of the difficulty. The other part of the difficulty is that in order to find out whether V is equal to 1.3 into 10 raised to 3 into I need to measure both current and voltage also, and there is precision associated with those measurements. Perhaps you can measure the current within a milliampere. The current may be 1 ampere, but within 1 milliampere. This is because of the nature of the instrument, the dial reading on the dial, or if it's a digital display, the number of digits that you have in the display. If you set it up in the ampere mode and it can go up to 3 places of decimals, then milliampere is the lower limit. You can't go lower than that. Of course, you could use a more precise instrument, or you could use a setup whereby you could measure the current within 1 microampere. And again, one can, if one wants to go further even and talk about nanoamperes. Similarly with voltage, volts or millivolts or microvolts, but ultimately there will be a practical limit where you will stop. So you will measure voltage, say, within 1 millivolt. The voltage will be of the order of a few volts, but within a few millivolts. Similarly, current may be of the order of 1 ampere, but within plus minus 1 milliampere. As a result, the resistance value, if you wanted to measure it this way, by finding out the voltage and the current and then dividing the voltage by the current, will have its own precision. Of course, voltage current method is not the only method of measuring the value of a resistance. In fact, it is not necessarily the best method, although it may be a simple method in principle. There are, in an instrumentation course or measuring instruments course, you would have studied some other methods or some methods of measuring resistance other than simply measuring voltage and current. But to come back to our point then, an equation like V R of t equal to R into I R of t with a particular value of R equal to 1.3 into 10 raised to 3, assuming V is in volts and I is in amps, an equation that we write for this physical device, here this particular resistor, is only an approximation or an idealization, and that's about all we can say. We don't know of any better relation, but at the same time we will not insist that this holds exactly to 10 places of decimals or even 3 places of decimals. One can sometimes use the word, and this is a little better word than modeling, and that is the word representation. So instead of saying that this resistance is modeled by V equal to Ri or Vr of t equal to Ri R of t, so this equation is said to be a model of the resistor, we could say that this equation represents the behavior of the resistor, with the understanding that it's only under certain conditions and it's only within certain limits that the equation represents the behavior of the actual resistor. In fact, right now I use the word model in a third sense. Earlier we talked about a model of an aircraft, a scaled down model, which is physically similar, works on similar or the same principle, but has a much smaller size, weight, etc. That's one kind of model. The other is what we just started with, that is the RLC circuit and the mass spring dashpot force or displacement source system. One of them can be said to be a model of the other, and in place of the RLC, of course, we can have an operational amplifier or analog computer system set up, which is a model of the mechanical system. The third use of the word model is when we say that this equation is a model of that physical thing, the resistor. Sometimes one uses the word mathematical model, implying, for example, that in this model or in this representation, what I have written, V equal to Ri, V and I are numbers, R is a number, there is a product operation involved, etc. Not much of mathematics here in V equal to Ri, it's really simple arithmetic, multiplication, and that's about all. We must distinguish models, in this case equations, from the actual thing. Same thing holds for the model aircraft. The model aircraft is only a model of the actual aircraft. If you want to fly from here to Delhi, you cannot use the model aircraft for that purpose. Similarly, if you want a spring to do something, you cannot set up a RLC EMF circuit and hope that it will do the work of a spring. The model is different from the system. The model is a model of the system. It represents the system or the device. The model is mathematical. In place of an equation, I may draw a graph. So V equal to Ri could be shown by means of a graph of voltage versus current. In fact, for some devices we may not be able to write down an equation so nicely. it is easier, and in fact that's what you start with, by giving a graph of the behavior of V and I. Such graphs or curves are known as device characteristics, and probably you have already come across them in connection with diodes, transistors and the like. The simplest and experimentally the simplest to obtain representation of a diode will be by its VI characteristic, a curve of V and I for different values of V and I. The equation for it may not be very easy to write. In fact, there is no nice single formula for the whole curve, as you know. Of course, one can, with some theory or from a purely practical point of view, find out an equation that describes some part of this characteristic and even use it. So in that sense, the VI characteristic is also a model, but it is still more a mathematical or an arithmetical model, in the sense it involves physical variables like voltage and current, and gives you the pairs of values of voltage and current that you may find associated with a diode or with a resistor. So when we use the word mathematical modeling, we can include such graphical methods also. In fact, they are useful, as we will see in control work. Very often one can get some idea of what is going to happen by drawing graphs or pictures, rough sketches even. So you don't have to really write down only equations and then find that you can't do much with them because you don't know how to solve them. So here is one device, resistor, for which there is this model V equal to Ri, or to be very precise, resistor voltage VRT equal to R into resistor current IRT. What about the another component in the circuit? It's the inductor. Now the inductor has a parameter associated with it, namely the inductance. The standard symbol for that is of course L. Just as the resistance is the parameter associated with the physical device resistor, inductance is the parameter associated with the physical device inductor. And once again, like the resistor, an inductor or a coil can come in different sizes and shapes and material and so on. Here are a few examples of inductors of various sizes and shapes, and of course various values of inductance. One can have an inductance with a small inductance value like a few millihenries, or one can have a much bigger inductor or coil with an inductance of the value of few henries. Just as you can have resistors with a few ohms resistance or resistors with megohms of resistance. Now just as in the case of the resistor, and here it's even a much stronger approximation, or one should say really a weaker approximation, much cruder approximation, namely the relationship between the voltage across the inductor and the current in the inductor is given differently. VL, and I will write here now VL of t. Once again, V voltage, L, because L is the standard symbol for the parameter inductance, VL of t equal to L, the inductance value, multiplied by, now this time it is not the inductor current as you know, but the rate of change of the inductor current, DIL dt, or to emphasize that the rate of change also may vary with time, DIL dt at time t, and later on we will use a somewhat different symbol which is not used in many books, but you may find it in a few mathematics books. We will write it also as L into D, D standing for the derivative operation, derivative of the current, so DIL, IL is the current in the inductor as a function of time, DIL is the derivative, the rate of change of it as a function of time, and its value at some particular moment of time t. So the representation or the model for the inductor will be VL of t equal to L into DIL of t, DIL at t. The voltage of the inductor is L times the rate of change of the inductor current at that same moment of time. Now this is not arithmetic anymore, because it is not just multiplication, but there is the idea of derivative or rate of change, and so to some extent this means that we have gone beyond arithmetic and algebra, we have gone into calculus. And in fact it is this kind of a thing that gives rise to a differential equation finally when we begin to model a system. It's because there are devices like inductor which can be represented approximately, somewhat crudely, but still it may be adequate for many purposes by means of a relation like this, which involves derivative. In electrical engineering, of course, one talks about this and the other relationship for the resistor as a VI relationship or VI characteristic. So the VI relationship for an inductor is given by V equal to L di dt. If I is in amperes, if the time is measured in seconds, so the rate of change of current is measured as amperes per second. If the inductance L is in henries, then the product L di dt will give you the voltage in volts. Now what about the third component, the capacitor? Like the resistor and the inductor, capacitors also come in various types, sizes, shapes, and capacitance values. Here are a few of them. What is the model or a model, a useful model for a capacitor? Well, it is given as IC of t, current I in the capacitor, so subscript C at time t equals C, the capacitance, multiplying the rate of change of the voltage associated with the capacitor, or dVc dt at t, or using the d operator notation, it will be C times d Vc t. Here again we go beyond arithmetic and algebra, we go into derivative or calculus. The current in a capacitor or associated with the capacitor depends on the rate of change of voltage associated with the capacitor, and is obtained from the rate of change of voltage. If the voltage is in volts, rate of change is measured with time in seconds, and capacitance in farads, then the current will be obtained in amperes. Now as you know, the value of capacitance or capacitors that one is likely to meet in the laboratory is not of the order of farads, but very likely of the order of microfarads, maybe 100 microfarads or 1000 microfarads, or even much smaller than that, a picofarad. But the farad named after Faraday is the unit, and therefore volts per second into farads only gives you current in amps. But if you took volts per second multiplied it by microfarads, you will get the current in microamps. Now I said that the approximation for an inductor, or the model for an inductor, VL equal to L di IL dt, is a crude approximation, or I use the word strong, and then I said that maybe one should say weak, because in many cases it's not really a very good approximation. Why? Well, because the inductor, or at least many inductors, involve a long length of wire. It's called a coil simply because there is a wire which is coiled or wound around what is called a core, some magnetic material, and so there is a good length of wire there. Now this wire is a piece of resistor also. it has resistance. Even if it is good conducting material like copper, still it's not a very thick wire and there is a long length of it, so it has a good bit of resistance associated with it. By good bit, of course, I mean not megohms, but it could be a few ohms. So this inductor is not just L, that is, it's not that current in it produces some magnetic flux in the core, and therefore the rate, the change in the flux will produce a counter EMF or an induced EMF in the coil, which is what this V is about, but it has also a resistive part of it, as it were. And so if one wanted a little better, less crude approximation or model for it, one possibility is to think of it as a series combination of a ideal resistor with an ideal inductor. And so write down an equation like V for the voltage as not LdIdt only, but as consisting of two terms, Ri plus LdIdt, where the term Ri is coming from or taking account of the fact that there is a lot of length of wire there, and the LdIdt part comes by taking account of the fact that the wire is wound round an magnetic core, current flow gives rise to magnetic flux, and change in magnetic flux leads to the phenomenon of a counter EMF or a back EMF in the wire, and so on. But once again, we have to remember that this is the model. Nobody has connected actually a resistor, so-called ideal resistor, and an ideal inductor in series to make a practical inductor. The practical inductor is wire wound around a coil. And how good this approximation is, V equal to Ri plus LdIdt, will depend on how you are using this inductor. For example, if the current and the voltage are not changing very rapidly, and by very rapidly again one has to mean something very specific. Let's say the voltage and current vary sinusoidally, maybe at a few hertz or a few kilohertz perhaps, then the representation like V equal to Ri plus LdIdt may be okay. But if I want to operate it at frequencies of the order of megahertz, and if I want to be very ambitious, gigahertz, then this model will be useless. It will just not be useful. So this emphasizes the fact that the model is not this device or the system. The model is only an approximation. It's crude. Unfortunately, we don't know exactly what the true model is. So in that sense, it's an approximation to something that we don't know, and we have to make use of it and see whether it gives you good results or not. If it gives good results, it's okay. If it doesn't, then our modeling was not adequate. We'll have to look for a better model, that is a model which will give you results which fit what one actually finds by experimentation. The last of the devices is the voltage source or source of EMF or electromotive force. For that, the equation will be V again voltage, E the symbol for the electromotive force, E like R, L and C, small e or capital E. Its value at any moment of time t is equal to E of t. And what do I mean by E of t on the right hand side? What is meant is that E of t is going to be some known function of time. For example, if I have this cell freshly bought, freshly prepared, not very old, then I can expect that this E of t will be nearly 1.5 volts all the time. So this E of t will be really remain constant as I operate the cell for a fairly long amount of time. So if I can say confidently about this piece, this cell, that look, the voltage across it is going to be 1.5, no matter how long you go, no matter what the t is, then VE of t equal to ET, and in this case ET equal to 1.5 volts, is a good model for the cell. And once again, we know that this model can cease to be good. If you use a cell for a long time, then it doesn't behave like this anymore. If you actually measure the open circuit voltage of the cell, you will find that it's not 1.5 volts, but it has come down to 1.4 volts or even less. And not only that, when you actually use it in a circuit, so when you have current in it, the voltage may be even much less than 1.5 volts. So that is something which is not written here when I write VE of t equal to E of t equal to 1.5. The claim is that this cell or battery will be described by this no matter what current flows in it, what value of current, and whether any current flows in it or not. Now that's certainly not true of a practical cell. From this small cell, you should not draw perhaps a very large amount of current. Its voltage will no longer be than 1.5 volts. Not only that, the cell can get even ruined. So maybe if you draw a current of the order of a few milliamperes or tens of milliamperes, as when you put it in a transistorized radio receiver, not one cell but maybe 2 or 4 of them, the current that the cell supplies would be of the order of few tens of milliamperes. Under that condition, if the cell is fresh, it has not been used for too long a time, the cell will be described by an equation like this. This is of course the simplest in the sense there is no arithmetic here. The voltage is just some number, in this case 1.5. Now, like the RLC, voltage sources also come in various forms. A cell of this kind, a dry cell, is one. In your physics course earlier, you have heard about the wet cell, the cell that goes back to volta in a way, or the cell with zinc and copper dipped in sulfuric acid or hydrochloric acid, and various other kinds of cells that you have studied earlier. But it could look quite different. A DC generator is also an example of this kind of a thing. Since we are talking about an electric DC motor which requires power supply for the field winding as well as for the armature winding, therefore a DC power supply. Now this DC power supply itself can be modeled under certain conditions by a simple equation like V of t, V of the source at time t, is equal to not maybe 1.5 volts DC but 230 volts DC. Now, like the RLC, this kind of an equation is referred to as an ideal characteristic. Of course, it's ideal in a different sense also. That is, if you could have something like this, then perhaps some things, other things would be very simple. So in that sense, this is something which is also desirable. And it is true that when you talk about a power supply, the power supply should be such that no matter what current you draw from it, the voltage should be guaranteed to remain at some definite value. In the case of the AC power supply, let's say 230 volts, it should remain in RMS value, the waveform should remain sinusoidal, and the frequency should remain at 50 hertz or 50 cycles per second. So in this sense, one talks about an ideal voltage source, but here the word ideal also means that the voltage of the source does not depend on the current. The source that we have looked at is a cell in which the voltage is constant as a function of time, that is, it does not change with time. But an ideal AC voltage source will have a voltage which is given by a different equation or relationship, namely V E of t equal to maybe 230 root 2 into sine 2 pi into 50 into t, where, as you know, the root 2 comes because 230 is the RMS value and 2 pi into 50 comes because the frequency is 50 hertz. So in order for it to look like A sin omega t, where A is the amplitude and omega could be called the angular frequency of the sinusoidal waveform, A is RMS value into root 2 and omega is 2 pi into the frequency as cycles per second or frequency in hertz. Now of course, on the other hand, I can look at the mechanical system, look at the various devices, write down the mathematical models for each one of them, and of course I expect that all of you will be able to do it, because the 3 particular devices that are involved here are all familiar to us. That piece of matter or a block which already one has called mass, implying that in its description a number will play a role. That number will be denoted by the symbol m for mass, such that a particular equation or a relationship hold between 2 variables associated with the mass. And what is this equation? Just as V equal to Ri in some sense goes back to Ohm, although he did not really write equations like this. Similarly, the equation that one writes today for a mass goes back to Newton, and that's the familiar equation F equal to m into A. But since the acceleration may vary with time, the force may also vary with time, one will have to write F of t, the force associated with the mass or acting on the mass, equal to the mass of the body multiplied by the acceleration of the body at that moment of time t. And because acceleration itself is a rate of change of velocity, and velocity is a rate of change of displacement or position, therefore ultimately we may write this as m dv dt at t, or therefore with the d notation m into d v at time t. And because the velocity itself is the rate of change of displacement or position, we could write this as m d square s dt square at t, or we could write this as m into d square s of t, where d square indicates that the differentiation operation is carried out twice successively. First you differentiate s, the displacement function or the position function, you get a new function, that's the velocity function. Then you differentiate that to get the acceleration as a function of time, that you multiply by the mass number m, that will give you the force acting on the mass or the body at any moment of time t. So here is a model, a mathematical model of the mass. Unlike the resistor perhaps, and even much more so unlike the inductor, we believe that this is a much better model. This is not as crude as the other models are. We believe that every body has a mass, and there is this kind of an equation associated with that body. But then, as you know, perhaps if you have studied or heard about the theory of relativity and so on, that one has to be careful when using this equation. In other words, there are situations when this equation no longer may continue to hold. Because I am not talking about the situation where the mass of a body, so to speak, changes as time proceeds. Because one could actually argue that it is not the same body. That is, the body itself is changing as time goes on, and so no wonder its mass changes, because it's not the same body. What could be a good example of what you think of as a body whose mass is changing with time? In fact, any device which consumes or uses fuel is a device of this sort. As you ride your motorbike or your car, fuel is getting consumed. So if you think of the car as a single body, and if we include the weight of the fuel as a part of that body, then the mass of that whole body is changing. As you drive the car or as you drive the scooter, the mass of the scooter as a whole is changing. Now, whether you want to say that the mass of the scooter is changing or you want to say the scooter itself is changing, although some parts of it remain the same, and strictly speaking one would be right in saying that the scooter itself is changing, because after all, if one looks at the fuel tank, one can see that the fuel level is going down. If you look at the fuel gauge pointer is going down. This is a home example, but a much more important example is provided by a rocket, because there the amount of fuel that the rocket requires to get itself up to a particular height can be a substantial part of the total weight of the rocket, that is rocket with fuel. And therefore, as the rocket ascends, there is less and less fuel, and therefore one will have to think twice before applying the equation F equal to ma. How to change this equation, that's a different story. But here is a situation when you are considering the ascent of a rocket and you want to be realistic about it, you have to take account of the fact that the rocket is no longer a body with a constant mass. And this is not because of any relativistic effect, that the body is moving at a high velocity, therefore its mass is not the same as rest mass and all that stuff. It is simply that fuel is getting consumed, and the fuel is a substantial part of the total mass of the whole package. Now, if you looked at the fuel tank separately and the rocket separately as two bodies may be connected together mechanically, because after all the fuel tank is housed in the rocket, then the rest of the rocket, the mass will remain unchanged, but the fuel tank mass, or the fuel and the tank mass, that will go on changing. That will be a different way of looking at it, but the equation F equal to ma will no longer be applicable. So even a time honored equation like F equal to ma, there can be some reservations about it. The question of precision, of course, arises here. You can measure mass within a gram. The mass may be a few kilograms within a gram, or within a milligram or a microgram, but somewhere you stop. You cannot be sure about the last milligram or the last microgram. And the two quantities on the two sides, force and acceleration, both of them also cannot be measured with any arbitrary amount of precision. Acceleration through displacement, let's say, displacement in meters could be measured to within 1 centimeter, millimeter, or even micron or a micrometer, and therefore rate of change of position or rate of change of velocity, acceleration, will be measured within a certain accuracy. On the other hand, the force in newtons will also have precision associated with it. I should not have used the word accuracy, one should use the word precision in this case. Accuracy arises when the instrument that you use is poorly designed, or it has some faults in it, or is not very carefully designed, or it could be replaced by another instrument which gives you a result which is closer to what you think is the correct one. Whereas precision is something quite different. Precision is almost inherent in all measurement, simply because we know that earlier we could measure things to within centimeter or within a millimeter, because if one uses a scale, then you can barely see a millimeter on a scale. But then some person by name Vernier came up with an idea that resulted in a Vernier scale, and using Vernier scale now you can go down to a tenth of a millimeter, something which you cannot see directly, but indirectly you will say that your length measurement is now precise within 1/10 of a millimeter. And if I combine it with a microscope and so on, I may be able to increase the precision even more, which makes us think that we have not reached the absolute end of it. We have increased the precision of our measurement. Presently this is where we stand, but we won't claim that this is the length is exactly equal to this up to 10 or 20 places of decimal. So f equal to ma therefore is an approximation or a representation of the body, which is good for some purposes and it may not be good for some other purposes. But for our mechanical system, let's say f equal to ma is an acceptable description or representation or model. What about the other two components, the spring and the dashpot? Well, here is a spring and here is a variety of springs of various sizes, of various natural or free lengths, various materials and so on. What about their model? It's interesting that like the resistors which differ from each other in appearance, the inductors, the capacitors, the bodies or masses, springs also which look so different from one another, all of them can be described for many purposes by a single common equation. And what is that? That is related to a law which is named after Hooke. So just as you have Newton's law, which is embodied in F equal to ma, you have Hooke's law, which will relate force to extension. That is, there is the idea of what is called the natural length or the free length of the spring and the actual length at any moment of time, because the spring is being stretched or is being compressed. And therefore, with some appropriate sign system, F will be given as k, small k, into the extension. The extension could be written as length of the spring at any moment of time, say L of t minus L0. 0 is to remind you that this is the length of the spring when there is no force acting on it, the free or the natural length of the spring. So if Lt is the length at any moment of time, L0 is the free length, then this difference is positive if the length of the spring is longer, is greater than its natural length, which means the string is being stretched, and therefore this extension, which is positive, multiplied by a constant which is the elastance of the spring. It is connected with the property of elasticity of the spring. This product will give you the force, in this case the force of tension. Somebody is pulling at the two ends or at one end of the spring. The force with which the spring is being pulled is given by an equation like F equal to k into Lt minus L0. If Lt, the length, is less than L0, which means the spring length is actually less than its free length, therefore the spring is being compressed. So this difference has a negative sign, and as a result the force also has an opposite sign. And therefore, if in the first case it was tension, in this case it's the force of compression. Somebody is pushing, squeezing the spring with this force, and of course I should once again put F of t, the force acting on the spring, the force of tension or the force of compression, is given by k, the coefficient k, into Lt minus L0, and the spring has two parameters associated with it. One is the free length of the spring and the other is the coefficient k, which is also sometimes called the spring constant, because it is associated with the spring constant, or the coefficient of elastance or elasticity of the spring or elastance of the spring. So that's the spring of the mechanical system. The third thing is the dashpot, with the symbol that we have seen already. Now one may not come across a dashpot very commonly as an explicit component, simply because what the dashpot does is to be found without really asking for it. The dashpot is based on the idea of resistance to motion, but of a different kind from F equal to ma, the force of inertia, so to speak. F equal to ma says that in order to accelerate a body, you need force. You don't need force to keep it in constant velocity, at a constant velocity. You need it if you want to change the velocity, either in magnitude or direction or both. In the case of a dashpot, dashpot will oppose any motion. But here is a practical dashpot, which you can think of really as a cylinder, not this one necessarily, but think of a cylinder with a piston at one end of it and with air under the piston, and assume that the piston moves in an airtight manner. Then obviously as the piston moves in, the air is getting compressed, so it offers some resistance to the movement of the piston. In place of course the air, one may have oil, and one has to make some proper arrangement and so on. For our purposes of modeling in this particular example, the equation relating two variables associated with the dashpot will be the force on what may be called the plunger of the dashpot. The other part of it is fixed, so it's the force acting on the plunger. This is given by a coefficient multiplying the velocity of motion of the plunger. So V of t into a symbol that will denote this resistance to motion of the dashpot. I'll insert a statement giving the actual name of this particular constant, since I don't remember the standard name for it. So this is something which we'll add in the video. So this is the equation for the dashpot. F at any moment of time t is equal to this coefficient into Vt, and as before, in place of Vt we may write d, the derivative or the differentiation operation acting on the displacement function ds of t. So these are the three components of the mechanical system: the mass, the spring, and the dashpot, with their models, which are all equations, which may be good for some purposes, may not be so good. And there is one more, namely a force source or a displacement source. Some external force may be acting on the mass or the body, or one end of the mass itself or the body may be moved physically by some other device and undergoes some displacement. So like the ideal voltage source, you may be told that somehow the position of the mass, say x of t, varies in this sinusoidal way with time. That is, the mass is made to move somehow in this fashion, move back and forth along a line. Or alternately, on the mass may be exerted a force somehow, maybe by something attached to it, or some remote force of attraction may be exerted on that mass, whatever way. That's the force source. That is, there is an external force acting on the mass which is guaranteed to behave in such and such manner, maybe a constant force, or again an oscillatory force, maybe sinusoidal or whatever. So that will be the fourth component of the mass spring dashpot system. And in fact, one can have a special situation and the corresponding situation in the RLC circuit also, namely there is no force source or displacement source, except that at what one may call the beginning, that is when you start observing things or start looking at the system. Typically we call it our t equal to 0 initial time. Start your watch or clock and start looking at what's going on. At this initial moment of time, Let us say the spring has been compressed. So somebody is holding the spring with his hands, compressing it, and then at t equal to 0, as he sees the watch strike 0, he lets the spring go, removes the force which is holding the spring in a compressed state. Then, as we can expect, the spring will vibrate. It was compressed, so it will expand. That's its property of elasticity, but unfortunately it will overdo it, or it may overdo it, so it gets stretched on its own, but that gives rise to a force of restoring force of tension, so it becomes compressed again, and so it may go on vibrating like this for quite some time before, after some time, the spring comes to a standstill with its natural length. So in this case, one would have put the external force source, the force source equal to 0. Similarly, in the RLC circuit, one may have the circuit initially, and there will be one more element, namely a switch. And I keep telling my students that this is one very important part of electrical systems, the switch. Without the switch, life would be difficult. If you could not switch off the fan when you did not want it, or you could not switch it on when you wanted it, life would be difficult. The switch is a very important device. So in the RLC circuit, suppose I had a switch initially and the switch was closed, and as I see my clock strike 0, or here it strikes 0, 12 o'clock or whatever, t equal to 0 I call it, I open the switch, or rather things will not happen if I do it, or something will happen, but I would like you to think about what will happen. But instead of this kind of a thing, we have this alternate arrangement where now what will happen is there will be actually two switches. There will be one switch and there will be another switch, and this one switch S1 will be opened at t equal to 0, and almost simultaneously with it this other switch S2 will be closed. S1 will be opened so that the battery or the cell is removed, and S2 is closed so that the circuit remains closed, RLC circuit remains closed, so that a current can flow in the circuit. If you do this, you do find that after you have opened S1 and closed S2, the activity does not stop immediately, and if one connects an ammeter in the circuit to see whether there is any activity going on, or if one connects this to an oscilloscope, one will find that indeed activity goes on in the circuit even after the source has been removed. Current continues to flow for quite some time, and under certain conditions the current may be in fact oscillatory. That is, it will go through positive and negative values and keep on oscillating for some time before the current becomes almost 0. So the force source, EMF source, could be set to 0, but the current, the circuit will have some initial current, the capacitor will have some initial voltage, and so on. So in other words, it's as if at time t equal to 0, prior to that you had an excitation or a force or something acting on it. After t equal to 0, you have removed it, but this earlier activity of the force put the system in some initial condition or initial state, whereby the system can pull on for some time before it comes to rest once again, before it becomes dead. So whether it's the electrical circuit where I close and open switches in a particular way, but the system, the circuit was earlier connected and carrying current, or in the mechanical case, I hold the spring in this fashion with my hands, and then I let it go at some moment of time and watch it oscillate before finally it becomes still once again. So a system may have a force source or an EMF source or a displacement source, or the system may not have, and still it may have some activity associated with it. Now, going back to the analogy, then I have set up, or I have written down, we have looked at the equations for the electrical components, the equations for the mechanical components. Do they look similar? Maybe yes, maybe no. For example, the inductor equation V equal to L di dt looks very much like the Dashpot equation perhaps, because F is equal to the coefficient into derivative of displacement. So if I take current to be analogous to displacement, then the voltage across the inductor is analogous to the force on the dashpot. This is one analogy, but maybe one can look at it differently. For example, if I look at the mass equation, then of course in F equal to ma there is no derivative, so it looks like V equal to Ri. But if I look at F equal to m dV dt, then it begins to look more like an inductor because I have a derivative. But if I look at the second model m d square st, then it's looking like something else altogether. There is a second derivative now instead of a first derivative. What about the electrical side? Do I have anything like that on the electrical side? Well, the answer is yes, because if I look at V equal to L di dt once again, and if I say that ultimately the current is the result of motion of some charge, or some charge at some place in the circuit is changing, or charge is flowing across some cross section in the circuit, then I becomes the rate of change of flow of charge across the circuit, or the rate of flow of charge across the cross section. If for charge I use the symbol Q, then current itself is the derivative of charge flow, and therefore voltage of the inductor will be L times the second derivative of the charge flow rate. Now this begins to look like the mass equation, F equal to m d square s dt square. So if I take displacement to be analogous to charge, then the mass becomes analogous to an inductor, and the force on the mass becomes analogous to the voltage across the inductor. So this analogy can be studied in several different ways. There are several analogies therefore that are possible. Now of course we have to think of putting these four devices, electrical devices together, or the mechanical components together to get the electrical circuit or network, or the mass spring dashpot with a force or a displacement source on the other hand, and continue with these equations of course, but write down some more equations whereby one will see that the analogy will extend further, and finally we may be able to write down one equation for the electrical network and one equation for the mechanical system. The two equations will look different. One will have voltages, currents, charge, maybe R, L, C, EMF. The other will have M, elastance, friction, or coefficient of viscous friction and whatnot, and of course displacement, acceleration, velocity, force. But except for these symbols, the two equations will look very similar to one another, and that's what will make the two systems analogous to one another, and therefore one will say that one is a model of the other. And in this case there is another word which has become very fashionable now, and that is the word simulation. Simulation. So one will say that the electrical network or circuit can be used to simulate the mechanical system, or the other way around, the mechanical system can be used to simulate the electric circuit or the electric network. And this works simply because both of them under certain conditions are described by equations which look very much alike except for a change of symbolism. instead of V I will have F maybe, instead of Q I will have S, the displacement. Time t fortunately is the same in both, but apart from that the two equations are similar or almost identical. Of course parameter values will be different. Instead of 1.3 into 10 raised to 3 I may have 10 there, and so on and so forth, but the two equations are similar. In fact they are of the same kind, known as a second order linear differential equation with constant coefficients and a forcing function. So in both cases we are led to this common model, a second order linear differential equation with constant coefficients and a forcing function or an input function.